Good day, everyone. Today, I'm excited to present my project on integrating the RISC-V processor with an FPGA, a significant advancement in the field of electronics and computer engineering. My name is Manoj Kumar. Currently, I'm in my final year pursuing electronics engineering, majoring in computer. My supervisor for this project was Dr. Lee Lini. The integration of processors on FPGA is a key research area. Traditional ISAs limit innovation due to their proprietary nature, while the open source RISC-V ISA fosters a more collaborative environment. However, integrating RISC-V with FPGA technology poses challenges, including a lack of comprehensive literature and guidelines, which obstructs its full potential. The primary objective is to successfully integrate the Neo RV32 processors onto an FPGA. For my project was the Intel Altera DE2i 150 development board. To demonstrate the processor's full capability, I've written a firmware on Holonomic X-Drive Mobile Robot. The implementation process involves several critical steps. The steps to configure and upload the Neo RV32 RISC-V core can be represented in a flow diagram for easier understanding. This is my overall diagram for my application. The RISC-V core is the main processing unit, which will receive data from the DualShock 5 controller via UART from an ESP32 and use the data to calculate the PWM signals required based on the inverse kinematics. I've added a custom VSDL subsystem for enhanced performance, enabling independent processing of encoded data for true parallel processing. This subsystem is directly coupled to the CPU with data can be accessible in the C code via registers. A timeout and a checksum mechanism is added for further improve in receiving the UART data reliability. So the CPU will always receive the correct data for real-time processing robot movement. I've derived an inverse kinematic from scratch to suit my application. Controller data is processed to generate the PWM signal for each motor, enabling real-time manual movement of the mobile robot without any delay. The second mode is the movement. The second mode of movement besides the manual movement, I've added a predefined movement control using encoder data, which will be processed using my custom subsystem in a PID loop. The robot can now move in a predefined coordinate system trajectory. Now I'll be demonstrating on the robot itself.
So now I'm going to demonstrate on the robot. As I mentioned before in the presentation, I'm using an Intel Altera FPGA board that is connected to an ESP32. These two microcontrollers is connected via UART to actually make the connections with a DualShock 5 controller. So we'll take all the inputs and all the processing will be done in this FPGA board. So motor drivers will be utilized to make the connections to drive all these motors, and the power source will be using these LiPo batteries. Okay, so now I'll be demonstrating first on the predefined movement. So in the code, I've set to move in a square pattern, 20,000 pulse for the encoder each. So forward 20,000 pulse, right 20,000 pulse, and then reverse 20,000 pulse, and go back to its position 20,000 pulse. So by pressing this button, the robot will execute the task. So forward, right, reverse, and go back to its original position. So now I'll be demonstrating on the manual movement. So by pressing the home button, you'll switch between the predefined trajectory or manual movement. So now with manual movement, I can utilize these two joysticks to actually move around. So since this is an holonomic drivetrain, we actually can move the robot in all directions without actually turning the orientation of the robot. So to change, I have assigned a separate joystick to actually turn around. So with combination of these two joysticks, we actually can do a few patterns. Also, I have assigned a separate button to actually increase the speed of the motors. As you can see, the data responds from the controller to the ESP32, and the UART connections between the ESP32 to the RISC-V core is very stable and there's no information loss. So thank you. This is my demonstration.